And if you have any questions, you should raise your hand. We can come to you. We can talk with you, and then help you, get things clarified. All right. I think that should be enough time for discussion. I'm going to close discussion in 5, 4, 3, 2, and 1. Right. Let's see how we did. Okay. All right. By the way, just to make sure everybody's on the same page, this is a line structure. When you convert line structure to a Lewis structure, we know that ends and bends are carbon. Here's a bend. Okay. Here's another bend, 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 and bend. All of these are carbon atoms. And then the common bond, carbon should have 4 bonds around it. That's the common bonding pattern of carbon. If you don't have 4 bonds, then you need to introduce carbon-hydrogen bonds to fulfill the common bonding pattern. Okay. So here we have 4 bonds around this carbon. Here we don't. We only have 2. Therefore, we're going to introduce 2 more bonds, carbon-hydrogen bonds. Same thing here, 2 carbon-hydrogen bonds. Okay. And then here we have 1, 2. We need to have another bond, carbon-hydrogen bond over here. And then here we have 4 bonds around this carbon, so it's fine. And then we just count, all right? And we count the number of carbons, hydrogens, and oxygens. And when you do that, let's see what we're going to get. We should, I cannot see this now. Here you go. Here are your responses. Most of us got this, and that's the correct answer as well. All right. What questions, concerns, comments do we have? Anything? Anything? Okay. Now, the other thing we want to worry about here is, give me a second. Let me have a question for that. Okay. Here you go. Here's another question. All right. Again, counting the lone pairs now. How many lone electron pairs do we have in glutamic acid? All right, again, if you have any questions, please raise your hands. We can come to you. Yeah, we have a question. Can I have the preceptors as well? Yes.
So,
all right, so that wedge just shows you a single bond coming at you from the plane. Okay, that is it. It is not a double bond. Double bond clearly have 2 lines like that. If you don't have that, then it is not a double bond. And usually when you draw a double bond, they draw on the plane so that you don't have to, show that coming at you or away from you. It's hard to represent that. All right, I'm gonna close this discussion in 5, 4, 3, 2, and 1. Okay, here are your responses. Let me see. Okay, still thinking. Most of us counted 9 valence, 9 lone pairs. That's the correct answer as well. Again, what we need to do is, let me have this, right? When it comes to determining the lone pairs, it's all about fulfilling the octet. All of the elements in this molecule should have an octet of electrons except for hydrogens. Hydrogens can only have 2, okay? So for example, if you take this oxygen, it has 2 bonds. That means only 4 electrons. We need 4 more electrons. That is going to come in terms of 2 lone pairs. Same thing here. We have 2 bonds. That means 4 electrons. Therefore, we're going to need 2 more lone pairs over here. And this nitrogen has 1, 2, 3 bonds around it. That means 6 electrons around it. We just need 2 more electrons, and that is going to come in terms of a lone pair. And then same thing here, 2 lone pairs around this oxygen, and the same thing over here. Okay, to fulfill the octet, that is it. And if we count the number of lone pairs here, it's going to be 9. Right? Any questions, concerns, comments, anything? All right, let's do another one now. Let's see. All right, what I want you to do is, I want you to determine the molecular geometry of the atom labeled X. Go. What's the molecular geometry of that atom labeled X? Is everything okay, Amanda? Okay. I just realized I don't have like an actual question here. So, and you don't have whiteboards either. Okay. All right. Anyway, what's the geometry of that atom X? Come again? Yeah, it's tetrahedral geometry. Okay. The reason is, let me clear my doodling one more time. All right. What we have here is a carbon. And then to fulfill the common bonding pattern of carbon, we have a carbon-hydrogen bond, so that we have 4 bonds around it. If we have 4 bonds or 4 electron pairs around it, that is going to be a tetrahedral electron domain geometry. And all these electron domains are bonding electron domains. Therefore, it's going to be molecular geometry is also tetrahedral. Okay, and that is how we know it's going to be a tetrahedral electron and molecular geometry. Right, any questions, concerns, comments? You should be able to do this, okay? That's the reason why, I brought this up. It's just a refresher, okay? All right, so that is the case. Let me remove that. Let's do another one. Here you go. Come that again? Oh, really? Yeah, I have no idea why. Do we have you here today? You, the TA? Okay, that's the only name I can remember anyway. Chidi is not here either. Nobody emailed me. All right. Thank you, Sybil. All right, so discussion is about spectroscopy. Okay, spectroscopy is about study of light matter interactions in the flavors of absorption and emission spectroscopy. Okay, the question is what happens during emission? What happens to the kinetic energy and the potential energy of electrons due to emission? Right? And just to give you some context, we explain this using the Bohr model of hydrogen atom. Right. So here's another thing you should do now. Actually, you should have your one-page notes out and try to use that to answer the question. Use them to answer the questions here. Okay. Have the one-page notes out. And if you find anything missing in your one-page note, make a note. You can add that. Make an amend. All right. I think there should be enough time. Okay, I'll keep this open for the time being. All right, the idea is, let's use the Bohr model of the hydrogen atom one more time. We have the nucleus in the center. Okay, here's my nucleus. All right, and then around the nucleus, we have what we call orbits. We have n equals 1 orbit, n equals 2 orbit, and n equals 3 orbit, and n equals 4 orbit, and so forth. Wow, it came out really, anyway, not that bad. Okay, now what's going to happen is during emission, the electron is going to come down from a high energy level to a low energy level. Okay, so let's say that our electron is initially over here. It can come down to n equals 1, n equals 4 to n equals 1, or n equals 4 to n equals 2 and then n equals 1. Okay, or n equals 4 to n equals 3 and then n equals 1, the ground state, and so forth. Okay, and when it comes down, the question is what happens to the potential energy and the kinetic energy. Now, when the electron is far away from the nucleus, you're going to have the weakest interactions. Okay, weakest interactions, weakest attractive interactions. That means highest potential energy. And when it comes back down, the electrons get closer to the nucleus. Therefore, the attractive interactions are strengthened by that. Okay, therefore, the potential energy is going to go from a high energy to a lower energy. That means potential energy decreases. And then when it comes to the kinetic energy, when the electron is far away from the nucleus, it is going to slow down. As a result of that, it's going to have a lower kinetic energy. When it comes back down to closer to the nucleus, it's going to move faster. And as a result of that, the electrons gain kinetic energy. Therefore, during the emission process, the kinetic energy increases of the electron. Okay, so the correct answer is potential energy decreases, kinetic energy increases. Therefore, option C. All right, what questions, concerns, comments do we have? Anything? All right, and then when it comes to the absorption, is the other way around. Max, oh yeah, we have a question here. Yes, please. Okay. Eva, go ahead.
Could you explain again why the potential energy decreases?
So we're talking about electrons coming from a high energy level to a low energy level, far away from the nucleus to closer to the nucleus, right, Eva? So nucleus and the electrons attract each other. When we have the strongest interactions, we have the lowest potential energy. When we have the weakest interactions, we have the highest potential energy. When the electrons are far away from the nucleus, you have the highest potential energy because the interactions are weakest. And when it comes back down closer to the nucleus, the interactions are going to get stronger, and as a result of that, potential energy decreases. Therefore, when you come back down from a high energy to a low energy during emission, the potential energy should decrease. Yeah? Yeah. Any other questions, concerns, comments? All right. Let's do, I'm going to clear my doodling here. Right, and then when it comes to the absorption, it's the other way around, right? Okay, it's going to be closed. The responses, the correct answers. Here you go. Let's try this question. Here you go. Again, this is a question from Unit 2. Okay, and this is about reading the mass spectrum. Go ahead. Thanks. All right, so Max is going to post Kahoot's questions on your D12 site altogether so that you can start reviewing them as well. It's going to be very useful. And also, he's going to be available next semester in my 152 class, which is going to be great. Okay. Anyway, we're going to have so much fun. Is that what you call them, Max? Kahoots? Something like that? You can use the microphone. It takes like...
It's on now. So I've made the Kahoots for each of the past exams. I'll post a link for all of those on D12 tomorrow. And then if y'all have any questions about like the final or anything, y'all can feel free to reach out to me this week. I'm studying for finals too, so I'll try to be responsive, like as responsive as I can. But if you have any questions, like feel free to email me. I'll leave my email when I post tomorrow too.
Perfect. Thank you, Max. All right, so let's try this question, okay? Anyway, in your actual question, in the exam you took, you were given the structure of lysine, right? I did not here, right? I thought that it is not necessary. It's not necessary, right? Is it? No, right? Yeah. So the only thing that we need to know is, okay, we are getting a fragment at 30. To get a fragment at 30, okay, we need to lose something. Okay, they're asking the mass of what is lost. All right. No, actually, asking what is lost. So to do this, what we need to know is the molar mass of the compound. What's the molar mass of this compound according to the mass spectrum? Come in again. Thank you. 75. All right. So that is given by this peak over here, peak furthest to the right. Okay, or the peak corresponds to the highest mass, gives you the molar mass of the peak. And then when you go from 75 to this peak, which is 30, okay, you are going to lose how much weight? Yeah, 45. 75 minus 30 is 45. Now, only the thing that matters to us is our fragment, our correct answer should have a mass of 45. That's all that matters. Now we're going to start counting. Okay, to do that, let's go back here one more time, okay, to our options, and let's start counting. Okay, so when it comes to the first one, we have one carbon, which is 12, and then one nitrogen, which is 14, and then 4 hydrogens. So 14 plus 12 is 26, 26 plus 4 is 30. This is going to be 30, 30 is not 45, so A is out. Option B, nitrogen is 14, hydrogen is 2, therefore this should be 16 altogether. 16 is not 45, therefore B is out. And then option C, carbon is 12, and oxygen is 16, you have 2 of them, therefore 32. And 32 plus 1 from hydrogen, guess what, that's 45, right? Yeah, this should be 45, therefore 40, this should be the correct answer. Just to completion of our thought here, thought process here, let me calculate the molar mass of this as well. This is 16 and hydrogen is 1, therefore this should be 17. 17 is not 45, therefore option D is not our correct answer. The correct answer is option C. All right, what questions, concerns, comments do we have? Okay, so if you are given a peak and then asked to identify the fragment that corresponds to that, you just use that molar mass. All right, for example, if the question asks you give me a second. If the question asks you for the fragment that corresponds to the mass at the mass peak at 30, what should be your answer out of these answers? A, B, C, and D. Thank you. It should be A. All right. Now the question is asking what should be lost. All right, and then we are losing 45. Whatever the fragment that corresponds to 45 should be your answer. Anyway, any questions, concerns, comments, anything? All right, so if that is the case, let's do another one. Let me clear my doodling here first. Okay, Let's see, I'm going to close this. Okay. Here you go. Let's try discussion. All right, calculating the energy. Okay, this is from the light matter interactions, specifically about the properties of light. Okay, using the particle nature of light, we were able to determine the energy of a photon. So all you have to do is determine the energy of the photon and then multiply that by the Avogadro's number to find the energy of 1 mole of photon. If you have any questions, please raise your hands. We can come to you, okay? Okay, so whenever we have to find the energy of a photon, the equation that comes to your mind should be energy should be equal to hc divided by the wavelength. Okay, here we are given the wavelength, and then we know the Planck's constant h, and then we know the speed of light c. We just need to plug and chug to get the energy of this photon. Okay, so let's do that first. Planck's constant is 6.626 times 10 to the power of minus 34 joule seconds, and the speed of light is 3 times 10 to the power of 8 meters per second, and then divide this entire thing by the wavelength, which is 220 nanometers. But we need to convert nanometers to meters, otherwise the units do not match. Okay, so to convert nanometers to meters, we need to multiply by 10 to the power of minus 9 meters, because that's how many meters we have in a nanometer. So nanometers cancel out, meters cancel out, seconds cancel out. You're going to get an answer in joules. What do you get? for the energy of a photon? Anybody who has the number for me? The energy of this photon in joules is, come that again? I heard that from somewhere. You just plug in these numbers, okay? Plug and chug in your calculator. If you do that, what do you get? You're gonna get okay, thank you. Okay, that's easy. So if you do that, you're gonna get apparently 9 times 10 to the power of minus 19 joules. Okay, this is the energy of one photon. Okay, but the question is asking the energy of a mole of photon. Okay, so what you need to do is you take this number 9 times 10 to the power of minus 19 joules. Okay, multiply this by the Avogadro's number, which is 6.022 times 10 to the power of 23, because that's how many particles you have or photons you have in a mole. Okay, and then this will give you the joules per mole, but they're asking in kilojoules per mole. So what you need to do is divide this by 1000, right? Because that's how many joules you have in a kilojoule. Okay, if you do that, joules cancel out, and then you're going to get the answer in kilojoules per mole. Okay. Now, in my experience, whenever you are in the visible range, all right, you're going to get a 3-digit number. Okay, and the only 3-digit number here is option C, therefore it has to be 541. Okay, and then it cannot be 10 to the power of minus 19. This is usually what we get for joules per photon. And then this number is too small. This cannot be. Option A cannot be. D cannot be. And between B and C, I know based on experience, it has to be 541 because we are in the visible range. Right? Any questions, concerns, comments at this moment? Anything? Okay. Let me see. I'm going to close this question then. All right. Here are our responses. All right. But anyway, if you have any questions, please let me know. All right. Anything. Because, I mean, you should see something like this in your final exam for sure. I mean, anything that we have covered in class is fair game. Okay. So here's my favorite protein. Not the favorite protein. The spectrum I get for the favorite protein. Okay. We have the absorbance here. We have the wavelength over here. And this is in nanometers. Okay. We have a 280 peak because it's a protein. All the proteins have a peak at 280 because of tryptophan and then other aromatic amino acids there. And also this particular protein absorbs light at 500 nanometers. It's in your eye. It's called rhodopsin. Okay. It absorbs 500 nanometers. Okay. Now the question is, so let's think about this peak over here. What I want you to do is I want you to calculate the frequency of the radiation that corresponds to this peak. Go. I want to see that answer in your I mean, you don't have whiteboards. In your notebooks. What's the frequency?
Or stretch.
So to tackle a problem like this, all we need to do is to use the relationship between the frequency and the wavelength, because we are given the wavelength, right? And that relationship must be frequency is equal to C over lambda. Okay, that's all you have to do. And then C is 3 times 10 to the power of 8 meters per second, and divide this by the wavelength, which is 500 times 10 to the power of minus 9 meters. Okay, so if you solve this problem, you're gonna get, I don't know, 6,000 something. I mean, six. It should have 6. Let me see. 6 times 10 to the power of, I'm thinking, give me a second. So it should be 14 per second. Yeah? Is that what you got? This is what you, perfect. Okay, there you go. All right. Any questions, concerns, comments about this? Anything? All right. Now we know how to tackle that. Okay, we knew that, but it's just a refresher actually. Now, you know what? Let's do another one. I think I'm going to do some unit 1 questions soon. Okay, let's do this question and then let's try to find a unit 1 question, okay? Don't forget about the survey, okay? Otherwise, I might forget about it. Don't let me forget about it either, okay? So, can I have somebody? Okay, I'll come to you, man. All right, please submit your answers. I'll give you about 10 more seconds. All right. Now, in this case, again, we're talking about the energy. Whenever we're talking about the energy and spectroscopy, okay, there's only one equation that should come to your mind, okay, and that is, let me see, okay, only one. Energy is equal to H C over lambda. Okay, instead of writing HC over lambda, I mean, I say HC multiplied by 1 over lambda. It's the same thing. Okay, now 1 over lambda is the wavelength. I'm sorry, the wave number. Okay, so what we have in the x-axis here is 1 over wavelength. All right, and as we can see here, energy and 1 over lambda are directly proportional to each other. Okay, or energy and the wave number are directly proportional to each other. Higher the wave number, higher the energy. Okay, so in this case, we have the highest energy peak for NH somewhere on here. Okay, therefore, that should correspond to the highest energy IR transition. That is it. Okay, higher the wave number, higher the energy, because we have a direct relationship between energy and the wave number. But when it comes to the energy and the wavelength, they are inversely proportional. Energy and the wave number are directly proportional to each other. All right. Any questions, concerns, comments? Anything? Elaine, did that answer your question? Yeah, perfect. Okay, so with that, let me clear my doodling one more time. What I want to do is, let me close this. Let's do another one and then, okay. Okay, let's try this question. Another one from IR spectroscopy. This time you are given the wavelength. And the question is, what does this wavelength correspond to? What peak? Is that the question? Yeah, which bond or what peak? Please, if you have any questions, let us know. We can come to you. Okay, so in the IR spectrum, you are given the wave number in per centimeters. Okay, that means the first thing I would do is to convert this wavelength, which is in meters, to centimeters. Okay, once I have that, then I will take the inverse of that to get the per centimeter value and compare that to whatever we have on the IR spectrum. Okay, so let's try doing that. To convert meters to centimeters, let me see if I can do it, right? I'm going to multiply this by 100 because that's how many centimeters we have in a meter. Okay, so the meters cancel out and then I'm going to get the answer in centimeters. This is 1.3 times 10 to the power of minus 3. Okay, and now I have the wavelength. This is my wavelength, which is lambda in centimeters. Okay, now all I have to do is take the inverse of that, which is 1 over lambda. So 1 over lambda of that should be 1 divided by 1.3 times 10 to the power of minus 3. And now I'm going to get the units of per centimeters. All right, I'm back. All right, so let's see how we did. I'm going to close this question in 5, 4, 3, 2, and give me a second. 1. Here are our responses. Okay, most of us pick option B, and option B is the correct answer as well. Okay, that means you should get less than 1,000. Okay, so obviously we need to divide 1,000 by 1.3. You're going to get 900 something with this per centimeters. Okay, all right, what questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? Okay, let's do another one. This time I want to jump to unit 1, if I may. Okay, let me see. All right, let's try this question. Here you go. Again, the best way to prepare for the final exam is going over the past exam questions, okay, and also the quiz questions. All right, that's the best way. And on top of that, I mean, if you run out of things to do, you should have past review exams as well, which is going to be another great resource. Okay, just go over them. That should be enough. Don't do anything else. You don't need to. The only thing you have to do is going over these past exam questions and past quiz questions and make sure that your one-page notes can answer those questions. That is it. If as long as you can do that, you should do great on the final exam. Okay. Again, if you have any questions, please raise your hand. We can come to you. All right, I think that should be enough time. I'm going to close this question in 5, 4, 3, 2. You know what? Let's keep it like that. Okay. Anyway, now here's the thing. All right, this is about the particulate model of matter. All right, and according to the particulate model of matter, the temperature is a measure of what? Thank you. The average kinetic energy. All of these substances are at the same temperature of 80 degrees Celsius. Therefore, they all should have the same average kinetic energy. Yes? Okay. Now, the tricky part is about the potential energy. Now, in this case, you are assuming the ideal gas behavior. What do you mean by, let me see your answers actually. Okay. We are assuming the ideal behavior. All right. I have a feeling only one of them is correct. Okay. Anyway, so what is meant by the ideal behavior? Anybody? Ideal means, Amanda? Thank you. No interactions between the particles. All right. So in the gas phase, if the particles are far apart from each other, then they are, we can assume that they are not interacting with each other. If that is the case, we are going to set the potential energy to what? If they are not interacting, they're far apart from each other, the potential energy is set to, anybody? What's the value for the potential energy? Thank you, 0. All right, that's our definition for 0 potential energy. All right, there are no interactions whatsoever. That means the potential energy is set to 0. That means all of these gases will have a potential energy of 0. Okay, and that's by the definition. Therefore, the correct answer has to be option D. They have the same average potential energy and the same average kinetic energy. Yeah, it's kind of a tricky one, but this is not the first time you are seeing this, by the way. This is directly from your Unit 1 exam, all right? This is just a refresher. Anyway, any questions, concerns, comments, anything? Okay. All right, let's do another one. This time, all right, let's take the same 3 gases. What I want you to do is I want you to arrange them from slowest to fastest. Okay, go. At 80 degrees Celsius or whatever the temperature is. By the way, what's the analogy did we use to explain something like this? Anybody who can remember the analogy? Come in again? Close though, but we use 2 famous companies. Thank you. Tesla and Nikola, yeah? Does it ring a bell? Okay. Tesla car versus Nikola truck, Nikola 18-wheeler. Which one should be faster if they had the same energy? That's what this question is about. All right, I think there should be enough time. I'm going to close. Oh, no, a little bit more. All right, there should be enough time, right? So it's all about determining the molar masses here. So out of these three, let me check the time here. Okay, we don't even have to calculate. That much here. I think the lightest molecule has to be which one? Thank you, the formic acid, because you only have one carbon and then 2 oxygen atoms. And then the heaviest must be what? Right? Yeah, I think the heaviest is propanol because you have 3 carbon atoms plus 8 hydrogens plus 1 oxygen. And when it comes to acetone, you have 3 carbon atoms, okay, only 6 hydrogens, and then 1 oxygen. All right, and then by 2 points, I think propanol is going to be heavier. Okay, that's all we need there actually. Okay, and the heavier one should move slower compared to the lighter one for them to have the same average kinetic energy. So the correct answer is option A. It cannot be option C. That's a typo. I will fix that. Anyway, what questions, concerns, comments do we have? Okay, the heavier truck should be slower than the Tesla car if they had the same energy. The lighter one should be moving faster. Okay, anyway, any questions, concerns, comments? All right, let's do another one. Okay, let's do this. Let me clear my doodling here. Okay, again, this is delta energy. Just ignore these weird typos over here. Delta energy versus temperature for C to A process. That's the question they're asking here. Oh no, you don't see the process here. Give me a second. Give me a second. Let's do this first. Here you go. Let's go back to that question later, okay? Because to do that problem, we need to know what the C2A process is. And to do that, we need the phase diagram, which wasn't there. So here's the phase diagram, which shows all these transitions. I'm not a particularly fan of this wording of this question, but but this was there in your first exam. Oops. All right, I'll give you 10 more seconds. Please submit your answers. All right, I think that should be enough time. Okay, I'm going to close this question in 5, 4, 3, 2, and 1. Okay. All right, here's the way we tackle this problem. Again, we are going from C to A. Okay, I don't care how it gets from C to A, whether it goes up and then go to A, whether it goes down and then go. I don't care about that. Only thing that matters to is when you go from C to A, the temperature has to decrease. Okay, therefore the kinetic energy has to decrease because you're going from a higher temperature to lower temperature when you go to A. Kinetic energy decreases, and also you're going from gas to a solid. Okay, in the gases we have the particles like this, far apart from each other, and then in the solid we have the particles closer to each other, closest to each other. And as a result of that, we have the strongest attractive interactions in the solid and weakest in the gas. Therefore, we are going to decrease the potential energy. Remember, the stronger the attractive interactions, lower the potential energy. That's the idea here. Okay, so both kinetic energy and the potential energy decreases during this process. Okay, and that should be your answer. What questions, concerns, comments do we have about this? Anything? Any questions? Okay, now I'm going to close that. All right, here are the responses. That's the correct answer. All right, now let's go back to the previous question we were dealing with. Discussion, here you go. Now again, what we're doing here is we are going from C to B. In this case, the path matters, all right? We're going from C to B first, and then C to B, you're going to decrease the potential energy. That's why delta is negative until you go to point B. I can even draw them here. So we are starting at C here, and this is B, okay? And then this should be A, and then this should be, let's say, B dash, and then let me call this A dash. Right? So that is around this vertical region. It should be around this boundary over here. Okay, because at the boundary, the phase changes, temperature remains constant. That's why we have a vertical line. Okay, since the liquid is becoming a solid, the potential energy decreases. The energy goes down vertically while the temperature remains constant, while until everything is converted to solid. Once everything is converted to solid, when you decrease the temperature, kinetic energy decreases, and that's why we have this line here. Is keep the microphone with Miley, please, so that we know we can do it together. Okay. So Miley, everybody, all right. Let's say that we are going from A to B over here. Okay. For this transition, okay, if we draw the temperature on x-axis and change in energy in y-axis, this is 0. That means below this is negative. Okay. So when you go from A to B, here's the temperature of A. All right. When you go from A to B, does the temperature change? While do you still have the microphone with you? Perfect. Has the temperature changed when you go from A to B?
No.
No, temperature remains constant. Okay. But Mary, so you see that we have converted the gas, which is over here, to a liquid when you go from A to B. Yes. Now, when the gas becomes a liquid, gases, we have the particles like this, far apart from each other. In liquid, we have particles close to each other. Where do we have strong interactions? In the liquid or in the gas?
Liquid.
In the liquid, we have strong interactions. Therefore, we should have a higher potential energy or a lower potential energy?
Lower potential energy.
Lower potential energy. That means we are decreasing the potential energy. Do you agree? Okay. That means even though the temperature remains constant, we are decreasing the total energy because potential energy decreases. Yes? Okay. Now, at this point, we are at B. Now, what we're going to do is we are going from B to C over here. All right. Now, when you go from B to C, we are changing the temperature. We are decreasing the temperature. Yes. If we decrease the temperature, what energy changes? Potential energy or the kinetic energy mainly?
Potential energy.
Or the kinetic energy. Because temperature is a measure of the kinetic energy, right? So if you are changing the temperature, okay, again, temperature is a measure of the average kinetic energy. If you are changing the temperature, which energy has to change?
Kinetic energy.
The kinetic energy has to change. Okay, so what's going to happen is when you decrease the temperature, the kinetic energy decreases. Okay, it's going to decrease like that until the boundary. Now, when we're at the boundary, let me call that X. Okay, there's a phase transition going on. So the liquid is becoming a solid. During phase transitions, what can you tell me about the temperature? Like when the water boils in your kitchen, okay, the temperature remains
Constant.
constant. Okay, same thing over here, right? So when the phase transition happens, temperature remains constant, but still the liquid is becoming a solid. That means potential energy decreases. Therefore, you're going to have a vertical line going down like this, indicating the potential energy decreases even though temperature remains constant. Yeah? Give me a second. Oh, are we about time now? Oh, shoot. Okay, give me a second. All right. Now, I mean, once everything is converted to solid, then again, when you change the temperature, again, the kinetic energy decreases. Therefore, you're going to have that line. Cadence, right? Oh, I'm cadence. What? Come in again? Melina, go ahead. Okay, yes, I got that feeling. Yes, let me have that attendance code, okay? All right, here's the attendance code for today. 6891. We'll do one last question, then we're done for today, okay? 6891 is attendance code. And if you're on Zoom, I mean, you can enter attendance code as well, I think. Okay, let's do one last question for today. All right, here you go. Last question for today. Let's see if we can get 90% correct answers. I know it has been some time that since we have dealt with the phase diagrams and then the phase transitions and delta E versus temperature diagrams, okay? That's why I brought this up today so that you can start practicing, start going back and then revisiting those questions so that you will be prepared for our last celebration on this Friday, okay? It's going to be Friday morning. It will be available from 7 to 10:30 a.m. All online on D2L. You don't have to be here, I mean, in person. All right. 15 more seconds, please submit your answers. All right, really quickly. Okay. So we have the lowest vapor pressure at any given temperature for acetic acid. That means it should have the strongest intermolecular forces. Okay. And on the other hand, when it comes to propanol, at any given temperature, it has the highest vapor pressure. That means it has the weakest interactions, weakest intermolecular forces. And then formic acid should be in between. That is it. All right, I'm going to close this question in 5, 4, 3, 2, and 1. And then here are our responses. And option C is the correct answer as well. All right, so when we come back on Wednesday, we will go over more of these questions and then some unit 3 questions. If you have any questions, I'll be here for another 5 to 10 minutes, all right? See you guys on Wednesday. Yeah.